That's all you get for the recording. Tough. Okay. Next one. Yeah. If you haven't watched any of the lectures, good luck. Oh, that was stupid. Yeah. If you miss class, you get to deal with it being blurry. Okay, so let's take a look at the first one. At a low pH, okay, or actually that doesn't necessarily give anything away. Whoops, it helps if I connect the computer too. Man, it really is Monday. So we're looking again at an amino acid. If anybody has to move into biochemistry, you can fully expect to see this level question, but scaled up significantly. In fact, I had a student who took biochem with me when I taught it here. And when he got into pharmacy school, they asked questions about it, and he couldn't remember, so he sent me an email asking if I would walk through it again for him, and I did. So I recorded another video that walks through the same chemistry. Connect. What the hell? Is it really that much of a Monday? No. Oh, maybe. There it goes. Maybe. We'll see. No. What that hole? Connect to your device. Connect your device. Well, you guys can see it on the board. But I was going to write it over here. Dang it. Fine. Let's see if it's just... Oh. You gonna do it? Thank you. Well, that was 3 minutes of nothingness. That's lovely. So to this question, what are we trying to do? What do you see when you look at that structure? Fine, I'll put it up on that screen. Man, I'm trying to get away with not doing it again. We'll call it green. That's fine. What do we see? One thing that I see is an irritating notation because they're showing it written out as a formula as opposed to actually looking at the chemistry. For those people being like, but Mike, didn't you write this question? Yeah, I wrote the question. I wrote the question to mimic how you might see it on an exam, and this is, or how you might see it on a standardized test. And standardized tests are written by people who insist on using typewriters, and so they don't draw out the structure. So you see something along those lines. So that might be the first place to start, is drawing out the structure so you can see your functional groups. Okay, within that, hopefully what you see or can acknowledge, pH equals 1, is that we now are concerned about some acid-base chemistry. pH 1, we're saying that we are in a very acidic environment. So if we're going to look at dropping a species, particularly a weak acid into the system, we've got HA in equilibrium with A minus, and if we're in an acidic environment, we would expect that structure to be primarily HA, because the acidic environment is now forcing hydrogens onto our structure. Does that kind of make sense? If we shifted to a basic environment, that's where we would see predominantly the deprotonated state, the A- state. Okay? What is this A? Well, that A comes back to our functional groups, and we have to be able to evaluate the acidity or basicity of those individual functional groups. So you should hopefully identify that there are 3 functional groups within that molecule. We have 2 carboxylic acids, and we have 1 amine. The carboxylic acid is generally the easiest one to approach because its chemistry is relatively straightforward. How does a carboxylic acid react? As an acid, which means it's starting in our drawing up here. If we were to equate the HA to A- system, our carboxylic acid is starting as HA. It then goes to become our A-. Whoops. Our conjugate base. Yeah? And for those people worrying, but don't you have a missing octet or something like that on that carbon, ultimately all I care about is the chemistry happening at the carboxylic acid. The rest of the structure is irrelevant. Okay, so we deal with one thing at a time. So I've got to decide something about the acidity of that functional group. Okay, since it's an acid, that could help me out, but I have to be a little bit careful. It's not just is it acidic, it's how is it acidic in comparison to the pH. So what I'm comparing is the pKa, the level of acidity of my functional group, and I want to compare that to my pH. Okay? That's what's establishing this line down here. If I am more acidic than my acid, then I'm going to protonate it. If I'm more basic, I'm going to deprotonate it. So I've got to decide. That comparison comes back to having memorized the pKa's. Okay? Or you could loosely run this based off of just your general interpretation. Okay? I have a carboxylic acid. Do we think a pH of 1 is more acidic than a carboxylic acid? If you don't know how to answer that, that's okay. What does that mean you need to do? Memorize your pKa. Okay? So you need to know the pKa of a carboxylic acid. What is the pKa for the carboxylic acid? It's about 4. Okay? It can absolutely get modified, but for the sake of these kind of questions, it's not that big of a deal. If you move into biochem, you won't be memorizing it as 4, you'll memorize it as 2, and I'll talk about that as well. Okay? So if we're at a pKa of 4, our pH is 1. Are we more acidic or less acidic? What's our relationship here? We're in a more acidic environment than the pKa because I have a smaller number for the pH. What does that mean? If I'm in a more acidic environment, what does that mean my structure should be? HA. What is the formula for our carboxylic acid? What is the HA for a carboxylic acid? It's OH. Okay. This question is asking, is it charge? Yeah, it's asking charge. What charge appears on our acidic form? None. Which means that contributes no overall charge. What about the other carboxylic acid? Same deal, no contribution. It's still a carboxylic acid. At a first approximation, your pH is fine, everything aligns, and we're okay. What about the amine? The amine becomes significantly more challenging to deal with because we have to know just a little bit more about its chemistry. Is the NH2 HA or A minus? Okay. It is the A minus. Okay. To the reference of it being both, sort of not really. Okay. When we're talking about the amine functional group, particularly in case of biochemistry, what you're looking at is the ammonium in equilibrium with our amine, which could theoretically be in equilibrium with the negative nitrogen. So when we go through and look at this and kind of pare this one down all the way through, we've got three different states, but we're only referencing HA or A minus. How do we decide where we're supposed to fall within this? That decision has largely to do with the meaning of pH. pH is based in a water environment. Okay? If we have a pKa that is larger than the pKa for water, that molecule doesn't exist. Okay? To remove that last hydrogen, we have to have a pKa of 35. Water will not allow the formation of that conjugate base. Okay, this is what's referenced in chem1, at least within our class, as the leveling effect that I said we didn't have to stress a whole lot about in chem1. Here's where it comes back and bites us. You can't have something more acidic than your solvent. You can't have something more basic than your solvent. The solvent provides a leveling system that allows us to run. If we think through OChem, we're like, well, we see NH2s all the time, or NH minus all the time. We've used that to deprotonate things. Yes, we have. In an organic solvent, not in acidic solvents. And the reason being is that if we try to dissolve that in water, what it's going to do is immediately deprotonate water, giving me hydroxide. So I don't have that species floating around. So when we're looking at the biochem reaction, what they're referencing is the pKa here for this molecule. So when we talk through biochem, what we're saying is HA goes to A minus, and this whole branch of that chemistry disappears. It's not that it doesn't exist, it's that it can't exist in a biochemical system. Okay? And the biochemical system still live or function. Okay? So the amine becomes trickier. We have to recognize its chemistry. The amine is primarily a base when we talk about its chemistry, which means we're starting at the A minus state and we'd move to the HA state. Okay? The pKa that's relevant is our pKa of 9. And what we would now go through and do is compare the pKa of 9 in comparison to our pH at 1. Are we in a more acidic environment or a more basic environment than our acid? More what?
Basic?
Oh, never mind, your pH is lower.
Your pH is low. We're in a more acidic environment, which means what state should we be looking at? We should be looking at HA. Which means when we look at the amine, the NH2 is not the valid representation for this molecule at that pH. We need to be HA. HA was protonated. What I would need to go through and do is put an extra hydrogen on it. The instant I put that extra hydrogen on, I also add a positive charge to the nitrogen, which now means the overall molecule is positively charged. Okay? We can get into much deeper explanations behind this. Ultimately, what you're pulling up is a bunch of content from 152. If you remember the Henderson-Hasselbalch expression, that's the derivation behind this on where that's coming from. Ultimately, all we really need to do is know our balance between HA and A minus. See if I can come up with a summary for it. We should be looking at HA when your pH is less than your pKa. And you should be looking at A minus when your pH is greater than your pKa. Okay. If you've got that nailed down, you don't have to worry about the why of where everything comes from because you'll never see it. How does this typically manifest in biochem? Or let's start with this class. It's going to manifest this way. You'll look at a simple amino acid and we'll say, what's the charge? Okay. To figure out that charge, you have to know the pKa's. That's required information for you to have memorized. Conveniently, there's only a few that we need to really memorize. Carboxylic acids and amines. Okay. Those are the big ones. Okay. There are a few others. We worry about those for biochem. Okay. And if it shows up on an exam, yell at me. That's fine. Okay. But then you need to look at the pH, which will be given to you in the question, and that pH can range all over the place. Okay? Depending on what your pH is, you're reevaluating these expressions to say what your state is. Kind of make sense? Regina, that was your question? Is that all good for you? Okay. People in biochem, typically what happens? Well, biochem has no patience for drawing out larger structures, admittedly for a good reason, because if we look at amino acids, we're looking at amino acids or proteins that are tens of thousands of amino acids. That's a very painful process to go through and deal with drawing out those structures. So instead they come up with shorthands. Right? Instead of saying the individual amino acids that make it up, they can use 3-letter codes. Okay? So we could use SER for serine. We could use HIS for, we could use, I don't know the code for that.
Isoleucine, it's ILE.
And as soon as you say it, like, oh yeah, I do remember that. And then we could do, and then we can do, okay, cool. And what we've got is a protein sequence. So what they could have you go through and do is say, what is the charge on this protein sequence at pH of 1? Okay, what does that mean you have to know? You have to know that when we write out our notations for our amino acids, there's an amino end and an acid end. Okay? But as I go through and do the protein, what happens? The internal functional groups get closed off into the backbone. So what's hanging out at this end is the amine. What's hanging out at the other end is the carboxylic acid. Well, that's not too bad. I just have to know the charges on those two pieces. You also need to know the serine has an R group that looks like yeah, I need some help. I don't know. What's the side chain for serine? Yeah, I don't remember either.
I'm an OChem, don't look at me,
It's
man.
like
SH, let's go with that. I think that's cysteine, but that's okay. Okay, so you would be responsible for knowing what the R group was on each of those. Okay, that extra chain. Once you know that R group, is that
Serine is CH2 with an OH.
OH?
There's no CH, it's just one CH2.
Okay. Is that OH acidic enough that it could be protonated or deprotonated within a water environment? So you would have to know its pKa. What is the pKa for an alcohol? Hint, it's the same as it is for water, which means I don't have to worry about it as being protonated or deprotonated. Okay? It's not going to affect the charge because it's not going to change when we change the pH. But you would have to do that for every single one of those amino acids, right? Yeah, that face is what I made too when I had to do this. Oh, right. Says the woman that couldn't tell me the structure for serine.
Okay, I'm also confused about how aspartic acid in pH of 1 is positive 1. Because I'm pretty sure it's actually 0. Like when you draw out the pHs and stuff like that, when you draw it out. That's why I don't understand, because I don't,
Yeah.
I didn't.
pH of 1, it's fully protonated. Yeah, it's a positive one.
But
I can tell you you're wrong.
that's okay. But,
Okay. So That's the process that you would have to move through. And of course, just to add a little bit insult to injury, do people like writing a bunch of letters?
No.
No, so instead of 3-letter codes, we'd move to,
What was that? There's 2 T's.
since someone got it, I'm just going to pretend that didn't happen, and we'll just erase all that. But that's the process that you'd be having to move through. Usually it just requires memorization. You memorize it for that one exam, and then you move on and never worry about it again. At least that's the general trend that I've seen, both from students that have gone through my biochem class and how I went through and dealt with biochem as well.
No biochem class here?
We used to offer it the instant we passed it off to somebody else to teach, because I really didn't like teaching it. It didn't have enough students.
I take it at
So-
ASU next semester.
I would also argue that if you are asked to take a biochem class for whatever prereq to get into some college or whatever institution you're trying to get into, you do not want to take it at the community college.
No. I validate that.
9 times out of 10, what they are asking for is upper division biochemistry, and the community college does not offer upper chemistry or upper division biochemistry. And talking to advisors, they don't understand that. So what'll happen is you'll take it and then you'll apply, and they'll be like, you haven't met the prereqs, and then you have to wait another however many months to go through that whole process again. So be very, very careful with that. So, which of the following substances can be subjected to decarboxylation when mixed with H3O plus and heat? Right? I think I remember this exact question when I took the ACS exam years ago. Okay. What is decarboxylation?
Getting rid of the carboxylic acid.
So D sets us up with the loss. Carboxylation, you're getting rid of a carboxylic acid. Okay. What does the carboxylic acid look kind of like? CO2. Okay. So if I was going to run through this process to make CO2, I would have those electrons come inwards because the hydrogen's acidic. Okay. But then what would be the problem?
Well, you'd be going over the octet.
I would exceed the octet on that carbon. Okay? When we're just looking at acid-base chemistry, that's fine. We just move the pi bond up. I'm not looking at trying to just remove a hydrogen. I'm trying to remove CO2 from the entire molecule, which means it's not resonating that pi bond. I need these electrons to move somewhere else. Where do I want those electrons to move? Towards the carbon or towards the void that I have drawn?
Towards the void.
Towards the void. Okay, which means those electrons need to go out with whatever's out there in the void. So what we're talking about is, can the void stabilize a negative charge?
No.
If we haven't specified anything about what the void is, so we don't know.
Well, just nothing.
Okay,
You can't-
so when we're looking at this structure, that's what we're aiming for. I need this kind of system of the carbon and the 2 oxygens. Okay. The hydrogen could become an issue. We'll look at that in a second. It is an issue. It is an issue. Okay, so we'll come back to that one. But what we're looking at is this void stabilizing a negative charge. Well, if it stabilizes the negative charge, what did the void act as?
Like there's a electrophile? Or,
Okay, so we could call it a nucleophile elimination, right? Because we're forming a pi bond and eliminating that molecule. That would be the name of the mechanism. What did the void act as?
A leaving group?
It acted as a leaving group. So really all I'm looking for this particular system is this C double bond O with the OH and a leaving group. If I've got a leaving group next to that, there we go, I can decarboxylate. Okay? That should scream problems pretty much right out of the gate. Okay? Because we can go through and say there's a carbonyl, OH, carbonyl, OH, just carbonyls. What does that mean? It's not going to work. I don't have that second oxygen that I need to make CO2. So that helps me out. We know D is false. D can't work because it doesn't satisfy those pieces. C does set me up with that carbonyl and an O, but instead of it being OH, it's OC. Okay, that could be problematic. Is there anything in particular that I should know from this unit about the relationship between OC and, resonance was the wrong arrow to show for that, OH? The correct answer to that question is yes. Yes, there is something I should know about that. I should know that that reaction can run under acidic conditions. It can also run under basic conditions. So in the presence of either hydroxide or H+, I can get that interconversion to potentially happen. Oops, I should do H plus OH up here. And in the bottom, I'd be doing HOC or OC minus. Kind of, sort of? Why is that useful? I said I wanted the carboxylate. I needed that CO2, OH. This ester didn't immediately fit that pattern, but I've remembered my content knowing that if I'm under acidic or basic conditions, I can convert that ester into a carboxylic acid, which then gets me the functional group necessary to do the decarboxylation, which means I cannot eliminate C either. Kind of, sort of?
And sort of.
Okay. So now the next part comes with the leaving group. Okay? I have to look at the ability of the rest of that piece or the rest of that structure to take the electrons. So we're looking at that piece existing for A. We're looking at that piece existing for B, and we're looking at, whoops, did I get an extra carbon? No, I didn't. That piece existing for C. Does that make sense? A doesn't look right. What do you mean? Say it again?
C is resonance stabilized.
Okay. Hopefully what we acknowledge that they're all negatively charged. We expected that pretty much out of the gate. Okay? So charge is irrelevant. We could then move to size, electronegativity. All of these are negative carbons. So all of them should immediately scream bad. Okay? They are same. Okay? They should all be like, these are horrible leaving groups. This would never, never happen. Okay? So that's size, electronegativity, and then resonance. And so what we should try to do in each of these scenarios is see if we can do resonance. Okay? For A, can I do that? Am I allowed to do that resonance? Yes, I'm allowed to, okay? And this, if you heard some of the people saying, yeah, you're allowed to, they didn't really say it emphatically or usefully, right? What's the problem with showing this resonance?
You broke it, Nick.
Well, we can deal with octet. That's a separate issue. What did you say, Austin?
So do you have two negatives?
No, we actually don't have two negatives.
It's still a carboanion.
It's not a carboanion. If you actually check charge, that's neutral. Octet is sort of an issue. We'll come back to that. There's a larger issue. What were you trying to answer?
Which would be the best leaving group?
The best leaving group.
Yeah, that's not.
The best leaving group needed to do what? Stabilize the electrons that it just accepted. Is that resonance doing anything with those electrons?
No.
No. Okay? So issues with that resonance beside, that's an irrelevant resonance structure. It's not addressing the electrons that need to happen for our leaving group. So I don't care about it. My focus needs to be that negative charge. Okay? For those people with octet issues, yes, there's an octet issue. okay, because it is missing its octet. It is not charged, and you can check that if you go through and do formal charge. It is no longer charged. What you've got there is what's known as a carbene, not particularly stable, and there's kind of other issues with it. Okay, so what we want to do is stabilize that negative charge. So what could we try to do? We could try to move it in there, but then what happens? You would exceed the octet on the oxygen, you'd have to kick the electrons right back. Meaning,
Bueno.
there is no, and this is where I might get a little more pointed, no useful resonance. How about with B? There's no resonance, period, with B. Okay? Though I will say very often I've had students do this and be like, well, what's wrong with that structure? Isn't that a valid resonance structure? You have to remember the implied hydrogen. So please watch out for those. This kind of drawing is explicitly drawn to trap students into saying I can do resonance. Okay? Make sure your starting structure has those implied hydrogens shown. We would have exceeded the octet, and that's why that resonance doesn't happen. Okay? Which then moves us to the last one, and as Aiden said half an hour ago, and I just chose to ignore, we do have resonance within this. That's putting the negative charge on the oxygen. Okay? Do we have now a stable leaving group? Yes. That's the system we now look for, and so our answer is going to end up being C. Kind of, sort of?
Kind of, sort of.
Okay. Are there memorization sheets for this? Because that's always useful to have something to memorize. Be like, just decarboxylation, I need to know this. Okay. That particular thing that you would need to know, if we clean up some of this other stuff that we don't want, is that when we're talking decarboxylations, what you're looking for is an alpha, beta, keto acid. Which is the higher priority functional group, the keto or the acid? The acid is at the end of our kind of referencing here. So there's my acid. We say alpha, beta. There's alpha. There's beta. What do I need to see at beta? My ketone. I now have an alpha, beta, keto acid. That's setting up the correct bond distance so that when those electrons come out or kind of come in, we can form our resonance stabilized leaving group. And we get the added bonus of CO2 bubbling out of the reaction. Okay? Kind of, sort of?
Kind of, sort of.
Okay. What next? I swear I did not do this, and every time I try to fix it, it just doesn't fix. Whatever. Delete, because that annoys me. So in this case, what we're asking about is energy diagrams, which I will say tends to be a good short answer thing because it's not an easy to memorize process because there's lots of different energy diagrams and reactions we could do. Okay? So if we look at our process here, we've got an energy diagram, energy goes up. We've got our reaction coordinate. The reaction coordinate is just referencing how our reaction changes. So we're going from reactant to intermediate to product, left to right, and we now want to predict something about kind of the energetics of each of these individual systems. So, start us off. Where do you think the reaction energy should be? as a hint, there is no quantification within this. Just somewhere in the middle. Okay? Because our intermediate and our products could both potentially be higher or lower in energy, and since we don't know where they're going to end up yet, pick a reactant that's somewhere in the middle so that you have both the higher and lower energy options. So there's our little well representing our reactant. Okay, we take a look at our intermediate. What do you think?
Higher.
Higher, why?
Charged.
Charged. Okay, so we can put our intermediate up here. Okay. Now what?
Lower than that, but how low?
Say it again?
Lower than that, but how low, because it doesn't have to charge anymore.
Okay, so it should be lower than the intermediate. Okay, good. But how low should we go? Should it be lower than the reactant or higher than the reactant? How are we going to discover that? Two approaches. Okay, both of them are tying back to stability. One, did you memorize the stability ladder? No? Well, shit. I guess we're going to have to actually rule our way through this or derive our way through that stability. Okay? So we're looking at our starting material and our primary reactivity that we're concerned about is the amide functional group. The rest of the carbon structure isn't doing anything, so we don't really care about that. And then we also have our carboxylic acid at the end. Where's our focus need to be for determining stability of these? Say it again? But I have to apply Cario to something. What am I looking at? O versus the N. Technically, you're going to be using Cario to apply to that, sort of. Where's the focus in deciding which one of these is higher or lower in energy? What's dictating that energy? Nope. It's not leaving group because neither one is really leaving per se in this. Though technically you could run that route too. What's the most reactive thing in both these molecules? The pi bond. The pi bond involves p orbitals, which is higher in energy. What we're concerned about is how that pi bond can change some of its energetics. So we could keep our focus there. What could that pi bond do? It could resonate, which means we're generating a partial positive down here in both of those cases. What we're concerned about is the stability of that carbon. That's going to dictate our energy ladder. Okay? Now we could go back and use Cario. Do they have the same charge? Yes. Do they have the same size?
Yeah.
Yeah, it's carbon versus carbon. They have the same size. Do they have the same electronegativity? Do they have the same resonance? No. Okay? The resonance is different. Why is the resonance different? Like, it's the same arrow, Mike. Why is that different? It's nitrogen versus oxygen donating those electrons. Which of those electrons is more willing to donate, or which of those atoms, sorry, is more willing to donate the electrons? Okay, well, what's the difference between nitrogen and oxygen? Electronegativity. Electronegativity is a measure of what?
Is how willing you're able to donate the charge.
Is that what electronegativity is?
Oh,
How much to donate electrons?
No.
No, that's where we're going to be careful. It's the complete opposite of that. Electronegativity is the ability to hold electrons or ultimately take electrons away from something else. So when we go back and look at nitrogen versus oxygen, oxygen is more electronegative than nitrogen. What does that mean about those electrons that it's trying to share? It doesn't want to give them, which means nitrogen is more willing to share, which means if it's more willing to share, it is what's better? Is it higher in energy if it stabilizes the positive more? Okay, that means our amide is lower in energy than our acid. I don't know why I'm writing acid there. higher in energy. We can now go back through. Here's our acid. We want that to be higher in energy. That was supposed to say higher. No one can read it anyway, so we just say it does. Than that, which means when we draw in our product, it should be here. If we were to continue out our diagram, we'd probably get something along those lines, and that should set up an issue. Would we expect this reaction to work? No, we're moving up on the reactivity ladder. That doesn't make sense. Okay? You could push to Emily's initial answer that she wanted to look at leaving group. We didn't draw the leaving group over here, largely because I straight up didn't want to have that conversation about it, but since you started it. Okay? We could compare a negative nitrogen to a negative oxygen. The oxygen is where we started. Our leaving group versus our nucleophile. Which one is more stable? The oxygen, which means what does our reaction favor? The oxygen side, the reactant side. Everything says the reactants are more stable, which means does the reaction occur? No, and yet it does. Okay? So does this mechanism accurately describe the conversion of an amide to a carboxylic acid? No, because we know it works, and yet the energetics scream it doesn't.
I feel like the term accuracy is like kind of misleading here because like I mean the mechanism shows correctly that it does, but it's the correct mechanism for it to work.
And so this is where there's lots of gray area, and I have to read your explanation to figure that out. So yes, people could go through and describe that the mechanism is correct, that all those pieces are there, and this accurately represents what's going on, as long as you don't then throw in the next line being that we know this reaction works.
Is it a bad way to think about it to just think of the induction causing the carbon to be more electrophilic or
On the product side, what you're doing is just playing fast and loose with the Cario system, which is fine, as long as you're correct. You got to be a little bit careful with that. So if we know this reaction works, what's the problem? What's that? And here's the fun part. Everything drawn in that mechanism is correct.
Well, then you're wrong. It's fine.
What did we end with? A carboxylic acid. In what kind of environment? Basic. What's going to happen? This reaction is going to continue to react. The student just didn't finalize this. The electrons come in, pick up the hydrogen, forming the carboxylate. Where's the energy of the carboxylate? The carboxylate is all the way down here. Why does our conversion from acid to or amide to acid work? It's because we aren't converting from amide to acid. We're converting from amide to carboxylate, which is the bottom of our tier. How do we get from the carboxylate back up to the acid? You add acid, okay? And that's how you navigate back up to the proper acid. Right? This is something walked through conveniently in the lecture videos, that if we watched the lecture videos, we might have seen that reference, because it's something that becomes very tricky, and it's what's capitalized on when we talk about the Gabriel synthesis. The Gabriel synthesis uses this exact thing to its advantage to ensure that we get monosubstitution, primary amines. That's the word I was looking for. That's really the only easy way to get primary amines, because what was the issue with our nitrogen? Multiply nucleophilic, which means if we just tried to run nucleophilic substitutions, we just substitute the hell out of it, and we get the quaternary amine, which at best sets us up to do a Hofmann elimination. If I want a primary amine, I can't just do a standard substitution. We have to navigate through something goofy, and that's the Gabriel synthesis.
Is the line of thinking with the carboxylase being lower in energy than the nitrogen or whatever, because it just has a negative charge and it readily gives it up?
So you can compare left to right again. At the very end, we're looking at a negative oxygen versus a negative oxygen. that difference, this one's resonance stabilized, whereas that one is not. Okay? Why is the carboxylate lower in energy than both of those? It started charged, so it's more able to share those electrons than those ones being neutral. Okay? Hopefully something that came out of this already is that having the ladder, the reactivity ladder memorized is a really, really good thing. And I would highly encourage you to memorize that because it makes it significantly easier to approach questions, and you can bluff your way out of a lot of systems if you just have that memorized. We good with that one? I answer your question? Okay. Next question? Full disclosure, I don't like this question. It's a fair question, but I don't like it. It's ACS fair, so yes.
Tomorrow fair. Or Wednesday
Tomorrow fair. I don't know anything about tomorrow. I can't answer that question. I genuinely actually don't know the answer to that question, to be honest. I don't have it memorized.
Did you already write the exam?
Yeah. It's already done. It's been done a while ago, yeah. Yeah, which is why I don't know anything about it. It's been done for a bit, and I have swiftly short attention span. Okay, so what does this mean? So let's address some of what's going on here. What do you guys see? Say it again?
Carbon next to nitrogen. So
Okay, so we could start looking at some of the reactivity, which is fine. What's the deal with all the arrows?
full stops.
Multiple steps. So this is trying to be nice, saying that we have 2 steps. So we get an A, we get a B, but what's going on with those next set of arrows? What's that?
Next to the bottom part, the top part, to get the middle part.
So we take A, B. What we're being asked for here is A, B, and C. How do we navigate all of those pieces? Okay. We could look beginning to end as well. Okay, what are we starting with?
Two things. Amide and alcohol.
I think you were answering the question I wanted you to answer. We've got an amide and an alcohol. Which of those is potentially the most relevant to look at? The amide. Why? It's a little bit borderline on the more reactive.
More obvious than it's easier to see.
What are you saying? Why do I care about the carbonyl? There we go. Looking towards our product. Our product shows that carbonyl chemistry, and if we recognize, hopefully, our patterns within this, what we've got is an anhydride. Okay? You don't have to know the anhydride, but you should recognize that pattern that we've drawn within there. Why is that now useful? We're starting with an amide, and we're trying to get to an anhydride. Did you memorize that reactivity tier? Yeah, it might be useful, because if we had that activity tier in mind, we start with the acid chloride up at the top, followed by our aldehyde, followed by our ketone, followed by our ester, which is on the same level as our carboxylic acid, followed by our amide, and then there's our carboxylate that says carboxylate. Okay? Why is that going to be useful for us? We want to end pretty much at the top, but we're starting pretty much at the bottom. We're going to have a bit of work cut out for us. Okay? In that memorization of that ladder, did you also happen to memorize how you could navigate up and down that ladder? Because there's certain reagents that would allow us to navigate up and down. Those reagents are going to become critical to allow us to get the proper pieces together to make the anhydride. All right? So, what do you want to try and do? What's that? Can we just jump the ladder? No, we can't jump the ladder.
No, it's just something to pull off the ladder.
Blow up the ladder? What? What are
Pull
you
it
saying?
up, like pull it up and look at it. I don't know.
Oh, you're asking somebody else to do your job?
I don't have an iPad, or a computer, or a laptop in front of me
Okay, so we've got our ladder, but what are the reagents that would allow us to navigate up and down that ladder? That becomes the important part.
You just look at solvents wrong or the
Okay? Said potentially another way, the only way we can get to the anhydride is by dropping down, which means at some point, what do we need? The acid chloride. What does the acid chloride look like?
carbonyl with the chlorine.
Okay? Which of our two functional groups looks the most likely to get to our acid chloride? The amide or the alcohol? The amide. Okay? Can I go directly from the amide to the acid chloride? No, what do I have to do? That's right, I need to go to the carboxylic acid first. How do we get to the carboxylic acid?
Get rid of the NH2.
Conveniently, if we scrolled up and looked at our answer work there, we had how we could navigate there, right? Didn't we?
Or like, what do you mean? Sorry?
The last question that we just answered, and we wrote down all the work, we started with an amide to get to a carboxylic acid. It's almost like trying to lead you into something. What did you add? Hydroxide. Hydroxide would allow us to get up to the acid. Then what do I want to do? I need to get to the acid chloride. For those people being like, can I go from the amide to the acid chloride? No, everything sits on the acid. To get to the acid chloride, that's that last step. There's only one reagent-ish that gets us there. That's SOCl2. We could have memorized that from this unit, or we could remember back in Unit 1 when we talked about SOCl2 that it converts alcohols, OHs, into chlorides. Right? So that's not new chemistry. That gets us to the top. Conveniently, how many steps did that take us to do? 2. Hydroxide, SOCl2. Right? I'm now at the acid chloride. I want to drop down to the anhydride. Which part of my anhydride do I have right now?
Wait, what? You have the carbonyl.
We have a carbonyl. The anhydride has 2 carbonyls. That's where we've ended. That's our product B. Said another way, is that the half of the anhydride that I have drawn? No. Is that the half? Oh, I accept almost. Okay. What would we need? We would need that oxygen, right? We would need the oxygen and the rest of this piece. This sets me up, right? All right, so now I could look at that second piece with my alcohol. How many carbons would I need in it?
3.
How many carbons do I start with? 3. So what do I have to do?
Put a carbonyl on
I have to somehow get a carbonyl on there. I need this, right? If I got that, everything's beautiful. I need to know the reagent that allows me to do that. What kind of chemical reaction do we do? It's going to be a little bit challenging here if we're thinking about our standard chemical reactions, our substitution additions, all of that, because if we go through and look at these pieces, we've added an oxygen and we have double bonds. So
Yeah.
this is going to get a little strange. How did we add the oxygen? Could we have just straight up added it to this?
No,
No? What else had to happen?
I had to get rid of the hydrogens that were there.
So we needed the reaction that gets rid of hydrogens and adds oxygens. What was that?
Condensation.
No.
Oxidation.
It's an oxidation reaction. We have 2 oxidation reagents.
One of them.
And it's one of them. If you don't know, guess and hope for the best. Okay? So let's go through and write down. We've got a suggestion for PCC. What's the other one? Chromic acid. There's 2 oxidizing reagents. Why do we have 2 oxidizing reagents?
One's a little selective,
One is selective. One would just do one oxygen and one hydrogen. The other one would just go whole hog all the way through. Which one do you think is going to be a little bit slower, tamer, perhaps not as funny? PCC. What did we want to do?
Slower. What?
Did we want to go slower?
Yeah.
No, we want to remove all of the hydrogens and replace them all with oxygens, which means
I thought you meant the other.
we want chromic acid. So if we remember that PC is politically correct, that can at least trigger some memory cells, hopefully say that that one's a tamer reagent. As a tamer reagent, that's not going to do the full oxidation we want. We want to go with chromic acid. Okay. Is writing chromic acid sufficient? Yeah, that's all I care about. You could also write any, like 50 other stupid references, formulas for chromic acid, and I'd accept that too. Fairly certain if I just saw CR, I would probably accept it. Just because I know there's a whole bunch of different ways to do the chromic acid. Make sense? Ooh, does that work? Okay. Again, that ladder is very, very helpful, and it can allow us navigate and move through things relatively quickly.
And that's how we get
Full points officially on this question if we just clean this up. That's full points. All it said is give me the synthesis. So all you need is the reagents. Would I be a little pissed? Yeah. Yeah. But if you had it memorized, you had it memorized. The rest of that space is to help you work through it, because I don't think it's reasonable to have you memorize everything. Other questions? Is that a question?
No, I was just like wondering, like, they're reacting together after they're modified with the
Yes.
essentially.
Yeah. There's a name for this process. I don't remember what it is. I used to call it combinatorial synthesis. It's not combinatorial synthesis.
That sounds fancy.
Conjugated synthesis. Converging synthesis. Something like that. I think it's a C word. Crap. Next question. I mean, that clock says we have 5 minutes. My clock says we've got 1 minute. Take your pick. What's that? 1 minute? Oh, that's fine with me.
We do smart work question?
Sure.
All right. Unit 4, chapter 13. Question 2.
Wait, unit 4?
U4, chapter 24. Basic E aliens.
That's not a public test. Bro, we're in 3.
That's due in December, bro.
Bro, what? Okay, wait, I was working top down and I was just chugging through it. I'm not paying attention. I'm like, I've never seen these reagents before.
That's why.
That'd be why.
That's why.
Hey, I was able to do some of them without.
So, yeah, and so since we don't have a whole lot of time, we can bright side it a little bit. I would argue Unit 4, while there are multiple chapters within it, 90% of it is resonance. The last 10% is memorization. Like, that's it. It's just those two pieces.
Yeah.
I'm sorry, I'm done, and I thought I had 3 more ahead of me. I'm sorry. No, it's good. Like, it's good news.
He was like stressing out. He's like,
but-
oh shit, it's due tonight.
Yeah, the next unit,
My bad.
I would argue significantly easier. I also say the last little bit of side news for that next unit. It is not useful chemistry. It will be on the ACS. You're not going to get a specific test on it, so you don't have to worry about that. It does make up probably 10% of the questions, so probably 7 questions.
Just like reaction with
Um,
aromatic rings.
Yeah, it's the reactions to aromatic rings, which, if we remember how we talked through all about aromatic rings, they don't react. They just,
How great that would be.
we just had to wait for the proper circumstances.
There's exceptions for everything.
Yep. So yeah, that's it. I'm gonna head to the tutoring center, so if you got questions, you can come chill there. If you don't have questions, you can go home
Are
and
you